Hello, everybody, and welcome to this extra lecture segment for 6838. In this particular lecture segment, what we're going to do is try to justify a formula for divergence of a vector field on a manifold that appeared in the previous lecture but wasn't really well justified mathematically. As you may have noticed in these little extra lecture segments, essentially I'm reserving those for the really ugly calculations that we do that I feel like are necessary for a complete story. In particular, one thing that you see a lot in introductory level geometry processing texts is the following definition. They say, well, the Laplace operator is equal to, okay, the minus is my choice. Not all books have that minus there. But they'll say, well, it's minus div of grad. Okay? And I'm going to put that in quotation marks. And the reason is that we spend quite a bit of time defining what it means to take a gradient of something on a surface, right? So ever since lecture 2 in 6838, we defined what it means to take a differential. And then in our previous lecture, we showed that the differential really is encoding a gradient vector. But then this other piece, this div, rarely gets a lot of love, right? So this definition is a little bit disingenuous unless we really carefully define both div and grad in a way that makes sense for functions on manifolds. Which is to say that our vector field is not defined on all of the extrinsic or ambient space, but just along the manifold itself, right? So we can't use the divergence of a vector field definition you're used to from vector calculus, because we don't have access to what it means for our vector field to be defined outside of this little thin slice through Rn. And so the goal of this lecture segment is to patch that issue together a little bit by giving at least, I shouldn't even say defining or rigorously deriving, but rather at least motivating a definition for divergence that I think both makes sense intuitively, just based on what we know about divergence, and also really at least convinces us that such an object is well defined. Now, our goal in this segment is not to be particularly rigorous. We're definitely going to use, what's the polite way to put it, like physicist style argument here and lots of pictures. But this is just to let you know that essentially the same as we can compute gradient of a function, we can compute divergence of a tangent vector field on a manifold in a reasonably well-defined way, at least when our manifold is embedded in Rn and when its metric is inherited from that ambient space. So we're not going to do the Riemannian version of divergence, although essentially it's going to kind of fall out of our argument anyway, but rather we're going to work with divergence of a embedded submanifold of Euclidean space, which is the main case that we've been working with in this course anyway. So to get started here, as usual, I have my notes hanging off the side of the camera here, so I apologize for looking over the side quite a bit. We're going to assume that we have a manifold M, which is embedded in Rn and is an M-dimensional manifold. Okay, and moreover, we have a vector field V, which is tangent to our manifold. So in general, when we talk about vector fields on a manifold, we typically are assuming that they're tangent. So we have a tangent vector field which in our sort of extrinsic version of differential geometry means that this is a mapping. So we'll say V, which goes from M to Rn, but this Rn is a little misleading. Really, what's going on here is that if we look at V of P, where P is some point on our manifold, then V of P is contained within the tangent space at P of our manifold. Okay, so like we can think of these as little, hairs along our surface or our higher dimensional manifold that are constrained to be tangent, right? And that's typically what we mean when we say vector field in differential geometry. Okay, so our goal here is to define the divergence of V, right? So typically this is written div of V, or if we're feeling fancy, we write that. Which, if you just remember your vector calculus class, what you would probably expect is a divergence of V goes from M and just assigns a real number to every point. Right? That's what divergence looks like. So remember that in flat space, right, in Euclidean space, the divergence of a vector field is like the sum of its partial derivatives. So it's like the x derivative of the x component of your vector field plus the y derivative of the y component plus the z derivative of the z component. The question is whether we can come up with an analogous formula for our vector field V. Now the challenge here is that the vector field V does not live on Rn. I can't like look off of our manifold and figure out what its value is. It only exists on this tiny slice of space, so all of our calculations have to live there. So hopefully we understand the basic setup here. Okay, so I'm already writing too big. I'm guessing I'm going to have to erase a bunch of times throughout our calculation, but that's okay. So let's draw a picture to get a basic setup. So first of all, the divergence is a local thing, right? It's basically computed just from V and its derivatives at the point P. So it's going to be enough for us to take a local parametrization around the point P, right? We're not going to need to consider like integrals over the entire manifold M or something like that. So in particular, we're going to work with a parametrization phi, right? This is the first of many things that I'll do that are a bit questionable if you wanted to do the most general version of this story. But in any event, let me draw the usual picture, which I hope you guys are getting used to by now. So here's our manifold on the right-hand side. I'll draw two-dimensional manifolds, otherwise known as surfaces, because those are the ones that are easiest to draw. Right? So here's M, and as we've kind of written above, M is embedded in some higher dimensional space Rn. And we have our point P, so he's living here, or she. And we're going to assume that we have a parametrization of a neighborhood around P, like that. And so that neighborhood has a pre-image under our parametrization, which will give the name phi. And we'll say the pre-image is some region over here. And just to make life easier, we're going to say that the origin is the point that maps to P. We can always do this. So, you know, P is equal to phi of 0. All right, so far we have our basic picture. And really, we have a vector field, which we can think of as like little tangent vectors that are living on our manifold over here. For example, if we're computing Laplacian, they're secretly the gradient of some function, but we'll actually do the more general case even when our vector field is not the gradient of some function. Okay? And so we can think of our vector field as a map from M into the tangent bundle, or which is in our case just embedded in Rn. Okay, so that's our basic setup, and so far our picture is pretty standard for this class. I don't think I've done anything too exciting yet. So again, our goal is to figure out what the value, or what a reasonable value of divergence for a vector field should be at our point P. The issue here is that I can't put an arbitrary point in Rn as input to our vector field function and get back a vector. I can only do that for points on our manifold. So the usual definition of divergence as the sum of partial derivatives in like x and y, you know, like all the different directions in Rn, doesn't quite work out. So essentially what our strategy is going to be is I'm going to take the vector field which is only defined on our manifold here. I'm going to come up with a vector field which is actually defined in like a little bubble around P in our space Rn, and then use the derivative of that vector field to compute divergence in the usual sense that you know from calculus class, and just restrict it back to the surface. That's going to be our basic trick here. Okay, so the first thing that we need to do is to draw some neighborhood around P that makes sense. So let's go ahead and do that. So first of all, we're going to compute a basis for not just the tangent space, but actually also the orthogonal space to the tangent space to our manifold. Remember, that's called the normal space. And we're going to give it kind of a funny set of labels, which is going to make sense in a little while. So we're going to write a basis And we're going to give it the name n bar here, which is going to be indexed from m plus 1 to n, right? Because these are all the sort of remaining dimensions that are orthogonal to our manifold. So these are all in Rn, and this is a basis for the orthogonal complement of the tangent space of our manifold. So this is Tp of our manifold orthogonal complement. And we'll assume that it is orthonormal basis, just for convenience. Okay, so the way I should think about these vectors is that they're pointing, 90 degrees to our surface here. Sorry, that was kind of messy. Oh well. Okay, so remember that our parametrization phi is mapping from, I guess this is Rm into Rn, right? That's how parametrization of an m-dimensional manifold works. We're going to extend phi to a parametrization of a whole neighborhood around P, including the remaining dimensions of our n. So we're going to extend our parametrization phi to a phi bar, which goes from Rn into Rn as follows. So essentially what we're going to do is we're going to take the first m coordinates of phi bar and just map them to the manifold. And then for the remaining coordinates, we're just going to move along these orthogonal directions. Okay? So in particular, what we can do is say we're going to define phi bar, which is a function of x1 to xn now. And what we're going to do is say, okay, well, for the first m coordinates, this agrees with our parametrization. So looks like that. But now, essentially what the remaining coordinates are going to do is kind of like move us off of the manifold M by moving in each of these directions, okay? So the way that we can write that is there's a sum k equals m plus 1 to n of xk times n bar k, right? So when all of the xk's are 0 for k bigger than m, essentially we end up with a parametrization of our surface. And then what ends up happening is now we've kind of made like little slices sitting on top of our manifold here. Okay, and this is useful because now everything we're doing is in n dimensions. We don't have to worry about the intrinsic dimension of our manifold. One thing that you can check, we're not going to check it here because this is a sloppy lecture, is that this phi bar is bijective, or at least injective, for relatively small x's. Okay? So let's at least write down what I mean by that. Oh boy, I'm going to run out of space way too quickly. So I'm going to hope that you guys are taking notes as you watch this, because we're going to have to do some erasing later. Okay, so in particular, what we can do is we can take small values of epsilon and r, which are greater than 0. And now we're going to consider this cylindrical shape. Or this, it's sort of a cylinder, but not quite. That's why it's in quotes here. And it's going to be defined as C, which we can write as the phi bar applied to some vector x with the property that the first m coordinates are in a circle of radius r. Okay, so the norm of x1 to xm is less than or equal to r. And then for all the remaining coordinates, we have xk is in between 0 and epsilon for k bigger than m. Okay, so let's draw a picture of what this looks like. So again, remember that phi bar is now a function of Rn into Rn, right? So it's mapping into our image space. The idea here is that we have our manifold, and we have our point P and a little patch around it, which is the image of a circle in our parameter space, right? So here is our parameter space. We're drawing a circle, and our circle is of radius r, right? So this would be phi. But then phi bar is also taking like in a space orthogonal to this plane. And the way that we can think about it is that it's sort of like taking this image on our manifold M and then lifting it to some like cylinder sitting on top of it, right? So this direction on top of our manifold are the images of the xk coordinate where k is bigger than n. Okay, and the basic point is that we're going to take epsilon and r to be so small that essentially this image is bijective, that we're going to take these to be really small values. Okay, so now what we can do, which is particularly sneaky, so remember we have our tangent vector field, but it's only defined on M. But unfortunately, we only know how to talk about like divergence and gradient when they're vector fields in Rn, like they're just vector fields in flat Euclidean space. So what we can do is now we can use this map just in this neighborhood around P to expand our vector field. So we can define a new vector field V bar of P, where P is in this sort of image, like phi of our small neighborhood here, which is going to be equal to V of phi bar, phi bar inverse of P. In fact, actually, let's not use P because P is the center of our neighborhood already. So instead, I'm going to call this, I don't know, X. Sorry, it's very hard to erase on these lightboard things. Right, so there's our expression. So to repeat, essentially what we've done here is we're going to say, okay, we have a vector field V, but it's only defined on the manifold. It's only defined on this little thin slice of Rn. So we'd like to extend it to this entire cylindrical universe around our point P. And so the way that we're going to do that is we first define this map phi bar. I'm realizing this definition is a little bit sloppy, but I think you guys can follow what I mean. So essentially, we have our vector field is only defined on the surface. We're going to figure out its projection onto M by moving along these coordinate directions, like these n bars here, and then just borrow the value of the vector at that projected point. And that allows us to have our vector field everywhere inside of this cylinder. Okay, so now we're in kind of good shape, right? We've managed to take our vector field on this manifold and then copy it into the ambient space. And the reason why that's useful is that we know how to compute divergence of vector fields in ambient space. We just don't know how to do it on manifolds. Okay, so far we've only written an orthonormal basis for the complement of the tangent space. Now let's write an orthonormal basis for the tangent space itself. So let's write an orthonormal basis E1 to EM, which are in the tangent space at P to our manifold. And that's going to be helpful in just a second, because essentially what we're going to do is we want to figure out what the divergence of our field should look like on the surface. We're going to do that by essentially computing the divergence in both of these coordinates at once. So in particular, now that we have this definition of an extended V bar in some neighborhood of P, we can talk about the divergence of V bar as follows, right? So just using the generic formula for divergence in Rn, what do we know? We know that remember the divergence is like the sum of the x gradient plus of the x component plus the y gradient of the y component, and so on. So here's a really fancy way to write that formula, which is as follows. We can say, okay, so this is equal to the sum from k equals 1 to m of ek dot producted with dv bar in the ek direction plus the sum k equals m plus 1 to n of nk bar dot dv bar in the nk direction. Okay, so let's think about this formula for a second and make sure you all agree with me. Remember in Rn what divergence looks like, right? So in Rn, right, the div of some vector field W is equal to the sum over K of like dWk dxk. Right, so this is a formula that you probably remember just from your calculus class, right? It's just saying, so for instance, in 3D, again, the divergence of a vector field is like the x derivative of the x component plus the y derivative plus of the y component plus the z derivative of the z component. One thing that you probably didn't check in your calculus class but should have is that if you rotated your coordinate system, that formula gives you the same divergence. And that's essentially what we've written here, right? So remember that the e's and the n bars together form a basis for Rn. And so this formula here is just saying that the divergence of this vector field in this region around our manifold is the sum of its partial derivatives. This is just fancy notation. But here's our sneaky trick. What is dv in the n-bar direction? Well, by definition here, our vector field doesn't change as I move along these n-bar directions, right? Because we defined our vector field to be the one where you project down along that n-bar and just borrow the value of the vector field. So what that means is that this is actually 0. Yeah? So what we end up with is that the divergence of this vector field, which is v extended to the space around m using a very carefully chosen formula, is really just the sum over the first k coordinates of ek dot dv bar ek, like that. And here's something kind of nice. Well, dv bar in the ek direction, well, v bar or rather ek is tangent to our surface. So this is actually identical to the sum k equals 1 to m ek dot product dv, where v is our original vector field in the ek direction. So what did we do? Well, if you'll recall from our previous lecture, this is actually equal to what we defined to be the divergence of our vector field v along the manifold. Okay, so the first thing that we've done so far in our discussion is justified that essentially our choice of divergence along the manifold really is kind of like copying our vector field to the space around the manifold and computing the divergence of that object in the extrinsic space. But that's a good start, but it would still be nice to have some geometric intuition for what this number is measuring. and that's what we'll do next. So here's going to be our trick. So what we're going to do is we're going to make use of the divergence theorem from calculus just applied to this cylindrical region here. So rather than having to come up with a new divergence theorem along our manifold M, this divergence theorem is going to be just the usual one in Euclidean space. And then what we're going to show is that specifically in this cylinder, the Euclidean divergence theorem actually tells us something nice about the vector field on the manifold. And so maybe, if it's all right, I'm going to erase just this little piece here so that we have a bit of space to work with. So let's pause and do that real quick. Okay, so now what we're going to do is we're going to apply the divergence theorem from multivariable calculus. Hopefully that one is familiar. But the trick, again, basically the whole idea of our derivation here is that we don't know how to work with manifolds, but we do have multivariable calculus at our disposal for regions in Rn, so we're just going to keep using that. So in particular, what does the divergence theorem tell us? Well, we're going to define this entire region. Remember that we've defined this cylinder to be C. Okay? So what we can do is say that the divergence theorem essentially is giving us a way to relate volume integrals in C of the divergence of a vector field with integrals on the boundary of C of the vector field itself dot product with a normal. So in particular, what it's going to tell us is that the integral in C of the divergence of our extrinsic vector field, right? So that's V bar, D, I'm going to say D volume. So this would be like, volume would be the measure on Rn, is equal to the surface integral on the boundary of C of Of the V dot the normal vector to C d area. Okay, so this is just the classic divergence theorem from calculus class. I haven't done anything with surfaces. Just C is some region in n-dimensional space, and just generically, when I integrate the divergence of a vector field in some region in space, it's equal to this boundary integral of the vector field dot product with the unit outward-facing normal. This is the divergence theorem from your calculus class, and hopefully we remember it. Okay, so far what we've done is shown that the left-hand side we can approximate for extremely, extremely small epsilon and r as follows. Essentially what we've shown is that the left-hand side here to basically zeroth order. Well, remember that the divergence of our vector field is really like the surface-based divergence of V rather than V bar, right? That's what we derived and then I erased, sorry. So the left-hand side is very, very coarsely equal to the following expression. It's equal to the divergence of our surface field at P. So we can say that's div of V evaluated at P, well, just multiplied by the volume of the whole cylinder here. So what is that going to be? Well, that's roughly, let's call this region on the surface C naught. So that's like just the piece of C that is actually touching our manifold. So it's like the area of C naught times, well, epsilon is the distance that we're allowed to move along each of our remaining axes, so it's epsilon to the n minus m. So this is like a zeroth order approximation of the left-hand side, right? So we evaluate the surface-based divergence at our point P, and then, well, it's integrated over the whole volume, so we just multiply that by the volume, which is roughly the area of the region on the manifold, just multiplied by the height. So in this case, like epsilon to the n minus m. This is where the extremely coarse approximations I talked about are coming into play. A more careful derivation would do this in some detail. So our next task is to deal with the right-hand side of the expression. So I'm going to deal with that here, and then eventually we'll erase it so we can get some space. So here's how we're going to do it. So let me see if I can draw a bit of a bigger picture here. So let's cut off some space. I remember my math professors in college doing this sort of thing and really hating it, but that's too bad. Okay, so here's our basic picture once again. So we have our manifold, right? Here's M. We have our region C naught, right, which is contained on M. Then we have a cylinder sitting above it, where the height if the cylinder is epsilon like that. Okay, and I'm going to give the cap of the cylinder another name. I'll call that C epsilon. And the remaining part, like the boundary of the cylinder, I'm going to call B. Okay, so if you think about it, the entire outer surface of our cylinder here is comprised of three pieces, right? C naught, C epsilon, and B. Okay, so remember our goal here is to approximate this boundary integral on the right-hand side. And now we're going to find that a really nice thing happens. Now, in particular, let's think for a second. So the normal to C epsilon kind of points up like that. The normal to C naught kind of points down like that. And both of these are basically orthogonal to the tangent plane of the surface. And then what's left is the normal to B, which is going to point, kind of outward like that. I'm realizing that this is tough to draw in the plane of our blackboard here, but the point is that the normals of C naught and C epsilon are kind of pointing like that, like off of M, and the normal to B is pointing tangentially to M. Okay, so that's our picture so far. All right, so what we can do is start with this boundary integral and then write it as three terms, right? So this is the integral over the boundary of C of V bar dot the normal to C over area. Well, that's really equal to the sum of three things. It's equal to the integral over C naught of this expression and C dA plus the integral over C epsilon of the same thing plus the integral over the remaining kind of cylindrical, toilet paper tube boundary, which is V bar dot and C GA. Okay, so now we're going to once again make an extremely informal argument because our goal here is just to build intuition. Now remember the C here is designed with really, really tiny r and epsilon. That's an epsilon, by the way. I'm realizing it's kind of ugly. And so let's think about what these dot products are doing. So remember that V bar is just our tangent vector field kind of lifted to the space around the manifold. And what is NC on C naught and C epsilon? Well, take a look. Well, clearly on C naught, NC, by definition, is actually orthogonal to the surface. This is in the orthogonal complement of TP of M, right? You can see that in the picture, right? So this is the NC. And remember that V on this is V bar and V actually coincide on C naught, right? Because there's no projection to be had. So, okay, what is this dot product? It's equal to 0. Okay, so the first term vanished. That's pretty nice. What about the second term? Well, it's basically exactly the same, right? Because again, remember, we're taking a tangent vector field and just kind of lifting it to slices above the surface. So if the height epsilon here is very small, this thing is basically tangent to our cylinder, and the normal to the cylinder still points normal to the surface. So this integral is approximately equal to 0, and it's easy to check that it goes to 0 very quickly as r and epsilon vanish. So really, all we're left with is this integral over B, this is really an approximation, of V dot NCdA. And this one does not vanish, right? Because here, V is tangent to the manifold M, and actually so is NC along B, right? Because B is the outer surface of this tube here. Okay, so what is this thing very roughly? Well, one thing that I could do is just take the boundary integral around this loop here, so like the boundary of C naught, and do a line integral of this quantity, and then just multiply it by epsilon to the n minus m, kind of like what we've done here. So this is like kind of just taking a zeroth order approximation, where we integrate along the loop, and then because our vector field is changing very slowly in the vertical direction, in fact, not at all, right, because we have this projection formula, this is really you can think of it as the following, which is epsilon to the n minus m multiplied by the integral over the boundary of C naught, which is now this loop downstairs, of the following quantity, which is just V. Now I don't need the V bar because I'm just in our manifold M, dot product with the normal to our curve. Okay, so this is going to be our approximation of the right-hand side of our expression. Again, remember we started with the right-hand side of the divergence theorem, and essentially what we've justified is that it very roughly looks like an integral on a loop on our surface, scaled by epsilon to the n minus m. And notice that V is our original vector field. I've managed to get rid of V bar once again, and NC is actually a tangent vector to the surface, right? Because NC is a normal vector to the boundary curve, but the boundary curve is a curve along the surface. So this is actually it looks like n, but it's normal to the curve, not to m. Okay, so again, we can write now that the right-hand side with this expression is very roughly equal to, you can say epsilon to the n minus m times this boundary integral where the boundary of C naught, which is a loop on M. Notice I've gotten rid of extrinsic space again. I was sneaky, of V dot NC dl. Okay. So now what are we going to do? Well, essentially, what do we have? We have that these things are roughly, the left-hand side and the right-hand side are roughly equal to one another. And as epsilon and r go to 0, that becomes more and more true. So, well, notice we have an epsilon to the n minus m factor on both sides here. So we're going to kind of isolate the expression for divergence here and then write it as a limit. So let me clear out things on the right-hand side here so that we have a little bit of space to write. Okay, so essentially putting everything together here, setting the left and the right-hand side equal to each other and taking epsilon to 0 basically leads us to a nice formula for divergence after moving area to the other side. So again, remember that essentially what we've shown is that there's two different ways that we can write divergence. There's the thing that we wrote as a definition in class without a whole lot of motivation, and now we're going to have a geometric intuition for what it's measuring. So in particular, what we can write is that the divergence of our tangent vector field, which does not need to be defined in the extrinsic space, which is great, evaluated at a point P, well, by definition, it's equal to the sum over from k equals 1 to m, the dimension of our manifold, ek dot dv of ek. Notice this is computable totally on our manifold without leaving the space around it. So this is kosher. And this is the definition we provided in class without a whole lot of motivation. But now, if we set these two things equal to each other, we can isolate div of v of p and take a limit. Then essentially, what we've coarsely justified, but turns out to be true rigorously as well, is the following formula. This is the limit as r goes to 0 of 1 over the area of C naught of r. Remember, that's like the image of a little tiny circle under our parametrization here, times the boundary integral of v dot the normal to C naught dl. Okay, and so if we kind of step back 10 feet and think about what that's telling us, notice that this formula here, for one thing, epsilon kind of dropped out because it ended up on both sides. So our entire construction was mostly just a mathematical convenience, right? So the picture that we can draw here, we have our manifold, we have some region, which is like C naught, and it's relatively small. We have our vector field, like that, and our P is kind of in between. Then essentially what it's saying is that this formula for divergence, this kind of opaque looking sum of dot products, is actually equal to a very intuitive thing, which is that this, what is this quantity? Well, v dot nc, remember that our normal vector is just is like a tangent to our manifold M, which is normal to the boundary curve C naught. There you go. So this is measuring the flux of our vector field out of this little tiny region, right? That's what this boundary integral is. It's the amount of v that's leaving this boundary curve. So essentially, what we've justified is a formula for divergence that says that it's roughly equal to the total flux out of our region relative to the size of the region, at least as a limit as that region goes really tiny around P. Okay, and so that's a really nice intuition for divergence. It pretty much matches our intuition for divergence in Euclidean space, and that's pretty sensible because essentially the way that we derived it was borrowing Euclidean theorems applied to this cylinder over here, and then just kind of restricting them to a very carefully designed vector field in Rn that turns out to be totally uninteresting in the directions orthogonal to our manifold. This also, even more coarsely, justifies isn't even the right word, motivates maybe, the divergence theorem, which we are not going to prove for vector fields on manifolds, which says the following. So let's say that I took my manifold M, and now I kind of repeated this argument, but rather than just on one loop, I took M and I divided it into millions of little tiny partitions, each of which had its own little boundary loop. So I take M and I divide it into just tiny little C naughts of R all over the place. If M is compact, I can certainly do this, at least for a fixed R. Then very roughly, what the divergence theorem says for manifolds is the following. It says if I integrate along M this scalar function div of a vector field, dA, so this is like a surface integral if M is a surface, this is equal to a boundary integral now along the boundary of M, so that's like these points, of V dot the normal to the boundary of M dl. You have to be a little bit careful how you define this normal vector direction. It points, this thing is actually tangent to the surface, but normal to the boundary. So it points out like that. And so very coarsely, you can kind of motivate this global theorem by copying this local formula a bunch of times, right? So you have a bunch of little boundary integrals, each one of which is roughly equal to divergence multiplied by the area of this region. So that's the left-hand side. And the right-hand side, what ends up happening, well, we've got two different copies of each boundary, right? One which is moving in one direction, and one which is moving the other, right? So you have one integral going up, one going down here, up and down like that, and they kind of cancel out. And all that's left is the integral along the outer boundary for our domain. Now, is this a proof of the divergence theorem for manifolds, which is just a generalization of the divergence theorem in Rn? No, it's the opposite of a proof. It's the world's least rigorous argument ever. But it is a convenient formula, and I think one that hopefully now is kind of intuitive. The idea here is that divergence is infinitesimally measuring how much our vector field is spreading out at a given region, right? That's what this limit is saying. And then what this divergence theorem is saying along a manifold is if I integrate divergence along the entire manifold, it's measuring the amount of stuff that's leaving the boundary. Okay, so if we step back really far here, essentially what we've shown is that our definition of divergence, right, which this is what it was at the end of the day in lecture, is kind of a sensible choice, and it corresponds to a nice geometric measurement about a vector field which is tangent to a manifold. And moreover, that interpretation, this limit here, really can be understood without looking at the space around the manifold, right? At the end of the day, this is a boundary integral that is restricted to the interior of a domain. And so this is just a nice way to understand divergence. I would say that the formula that we gave in class is kind of opaque. Really, the sort of morally justified thing to do would be to start with this natural quantity, which is measuring how a vector field spreads out, right? That's what this boundary integral is, and works backward. But hopefully now you all kind of see that all of these different pictures are roughly equivalent. Moreover, this limit formula motivates the divergence theorem globally on a manifold by just combining lots of these little local neighborhoods together. Okay, so hopefully you can see why we deferred this to an extra lecture segment, but I think this really completes our definition of the Laplacian, because now it's totally fair to say that we have defined both divergence and gradient in fairly, not rigorous, but at least careful way. Moreover, these integration by parts formulas that we were using in lecture are really just byproducts of things like this divergence theorem that I've written at the very end. Okay, so with that, next time we'll talk about how to make the Laplace operator work on a discrete domain like a triangle mesh or a point cloud. See you then.